Cool. Welcome everyone to our, I guess, inaugural CU Prime talk of the semester, if you don't include the debate, which we had. We are very fortunate today to have Seth Grable giving us a talk today. If you don't know what CU Prime is, we are a student organization designed to increase equity and inclusion and diversity on campus, and specifically in the physics department here, and just increase communities. One of the ways that we do that is through this talk series. And so we have grad students present their research in a way which is jargon-free and accessible, and we get to hear about cool lives of grad students and cool research getting done. So for everyone in the room, if you haven't signed in, our laptop is not working, but we have a QR code, so I'd ask you to scan that, and feel free to grab lots of pizza throughout the talk. If you have any questions for Seth, feel free to interrupt, and we'll have time for discussion throughout. With that, let's start. Please join me in welcoming Seth.
Cool, thank you, Tyler. So how many people did go to the debate? What did you guys think? Which side are you on? Yeah, so I think they're both fundamentally wrong. And the reason is because, you know, the Schrodinger picture is non-relativistic, and observables evolve as operators, but time, the thing it's evolving under, is not an operator. So it's an inconsistent theory. So I do work in quantum field theory, which is a fully relativistic quantum theory. And particularly in thermal field theory, there are no operators. So I hope to get to that by the end of my talk. But so there are no states in the formalism. So I don't know, sort of interpret that however you want. But let me get started here. Okay. This is my talk. What is entropy? That's all I really want to talk about today. I know most people usually do sort of, this is my research at large. I'm just picking one word from a publication that I did, one word from the title, and focusing on that word, because I think this is a really interesting topic, right? What is entropy? And I was very confused as an undergrad and heard lots of different concepts about what entropy is. And I feel like my version of it is my favorite. So I also feel like everyone is exposed to entropy very early on, because as early as chemistry, they start talking about entropy, right? So almost everyone should have some wrong idea in their head about what entropy is.
Except you.
That's right. So fun facts about me. Oh, I'm supposed to talk about me before these fun facts. Before these fun facts, I didn't do anything academic until I was 26. My path is very non-traditional. I basically played music. I was a construction worker. I have a rap album. You think my rap album's a joke? Who was laughing? Cool.
You have your mixtape on SoundCloud?
No, it's private. I'm from Akron, Ohio. I grew up down the street from LeBron. I don't know. When I was 25, I decided I was bored with life and wanted to learn physics. So I sat down and taught myself algebra through calculus and most of Phys 1, a little bit of Phys 2 over a summer, and tested into the University of Akron. And then from there, I went to Case Western Reserve. I transferred after 2 years after I sort of did all of the math and physics courses that they had available, because it's a small sort of crappy school. Then I went to Case Western Reserve at the same time that Tyler did. We didn't hang out there, sadly. He didn't like me. But during this summer, I was teaching, and I see him in Duane, and it's one of those, I just can't stop staring because you look so familiar kind of a thing. So I went and asked, I'm like, did you go to Case? And he was like, no. He was like, yeah, I went to Case. And then so I guess that's kind of how I got here. Also, okay, so I went to Case, and then I went to Oxford. At Oxford, I studied what they had the debate about last week or 3 weeks ago, whatever, right? I studied quantum foundations and all of that stuff. So I guess I have opinions about those things. However, like I said earlier, I think it's kind of all wrong. You shouldn't study the Schrodinger picture. You should study quantum field theory. You'll have a different view of quantum mechanics. And then from Oxford, well, okay, the pandemic hit, and then during the pandemic, it was hard to get into grad school, but I got into Mines, and then I hated my advisor at Mines. If he's listening, yeah, I still think you're a fraud. I was really interested in learning quantum field theory, and so I emailed Paul Romatschke, and he let me audit his class, and then next thing you know, I actually taught quantum field theory at Mines. And then the next thing you know, I got hired as a lecturer here to teach Phys 2 over the summer. And then Boulder was really desperate. Obviously, they were, hiring grad students from Mines to teach their classes. So they were like, we got to cover our tracks. So they instantly transferred me as a PhD student over here. So that's how I landed here. So that's about me. I play the drums. I have pet clownfish. I went to Oxford. It was during the pandemic. Oh, fun fact. You know who else was in England during the pandemic?
The Queen.
RIP. No, Isaac Newton, different pandemic, right? Theory of gravity and stuff. All right, whatever. Okay. Cool. Enough. So here's my paper. Interacting CFTs for all couplings, thermal versus entanglement entropy at large N. This is my first paper that I did with Paul, sort of on my own accord, as I was, how I put it, cheating on my research advisor at Mines, right? Because I knew what he was trying to have me do was fundamentally not good. So anyways, none of that should really make sense to you. I just want to talk about, like I said earlier, entropy. So, here's pretty pictures. Here's entanglement entropy on the boundary of a surface and so embedded in some space, right? Blah, 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 blah. These are thermal entropies I've calculated in 3 + 4n dimensions, right? For conformal field theories. Good stuff. But still, the main point is, what is entropy, right? Why are we studying this stuff at such a high level in physics, right? If you look at the ADS CFT correspondence and blah, 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 stuff with black holes, they're calculating the entropy of a black hole, right? What is this entropy stuff? So that's what I want to talk about. So before I do that, I've been told that you should all discuss amongst yourselves what you think entropy is, or some brave soul should raise their hand and tell me what they think entropy is. Literally no one is brave. Brave soul number one, go.
I'll come with that answer. I'll say it's like the irreversible loss of information.
Yeah, sure. Anybody else? I mean, what is information?
Some sort of ordered state, knowledge of where it is. So,
Well, all right, you already get to talk. You can just leave. Anybody else? No? Yes?
Say it's moving towards a more disordered state or chaotic state.
Yeah, something like. Do you guys know like why? Why is it doing that? Why are we always going towards these most complicated states? And why does the most complicated state have the most information?
my high school physics teacher said something about thermodynamics.
Okay, something thermodynamics, right? Yeah. Okay, good. This is good. This is exactly what I want to clear up today. This idea. Right. Anybody else? No? Aiko?
How easy it is to compress a file on your computer.
Bingo. Literally. Okay, let's get to it. All right, well, entropy can be used to describe, and this is from Wikipedia, but also from my own experience, right? Chemistry, okay, I remember learning about it then. Biology, economics, social system, information systems, quantum mechanics, cosmology, black holes, and the beginning and the end of the universe. So I would say that's basically everything. Entropy is very important. It's this, unifying concept among all the fields of science. So we want to talk about exactly what that is. It did start in the 1800s with Boltzmann as this something thermodynamics, right? However, then von Neumann came up with his own sort of idea about quantum entropy, and then Shannon came up with this idea of entropy that has to do with data compression. And Shannon asked von Neumann, like, what do you think this is? And something along the lines of von Neumann said, well, if you don't know what it is, just call it entropy. That's sort of how the fairy tale goes. So what is it? Okay. So we're going to do a thought experiment to understand entropy. And to understand that thought experiment, you need to know how to add fractions and you need to know what a logarithm is. So quick review of logs. Logs undo exponents, right? So what is log 2 of 4? Anybody? Go. 2, that guy says 2. What's log 2 of 16?
4.
4. What's log 2 of 8? Julia. Julia, what's log 2 of 8? Julia, what's log 2 of 8?
2.7.
Huh?
No, 2.7.
3.
Approximately.
2 to the third. Log 2 of 8
Yeah, so.
is 3.
Oh. It wouldn't be.
2 times 2 times 2, 2, 4, 8.
I should know
Huh?
this.
3 moves in 2048.
Yeah. Okay. Now, this is the beginning of our thought experiment. It's an Alice and Bob night out, right? So I say this is an exercise in communication. Alice sends Bob a message containing letters A, B, and C. Alice notes these letters have a probability distribution, meaning A shows up in the message a half, 50% of the time, B shows up an eighth of the time, C a fourth, and D also an eighth. You may notice that it equals 1. So it's a normal, normalized probability distribution. Good. Okay. Now, Alice is coding her message with bits. So she's going to code A with 0, 0, B with 0, 1, C with 1, 0, and D with 1, 1. Okay. Does that make sense? This should make sense so far, right? Nothing crazy. So how long is her message is sort of the question we want to ask. And then we want to ask, can we make it shorter? Well, clearly each letter here contains 2 bits. So the average number of bits in each letter is 2, right? Does that make sense? Okay. So here's an example. Here's her message that she's sending. So we have 4 A's, so they show up half of the time. Good. Then we have 2 C's, so they show up a fourth of the time, and a D and a B. Okay, look, our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, 16. And there's 8 letters, so the average length of each letter in bits is 2. Good. So now my question to you guys, and this is what Alice had to figure out, is how can she make her message shorter? Anybody? But I want to know explicitly how she's going to send her message, right? Yeah, some kind of compression, but how does that compression work? Yes.
What if you just assign a specific number to each letter?
Well, then we wouldn't be working with bits. We wouldn't be working in base 2. So that doesn't necessarily work. It's a good idea.
Could stick like a 0 and then the number of zeros after it, and like a 1, then like number of 1s after that, like you encoded base 10 decimal, or it's binary as appropriate.
That still would make it not base 2. Yes. Julia?
Make the most common symbol the shortest.
Yes, make the most common letter the shortest, right? So if there's something that shows up the most frequently used letter should be the shortest. And then the least frequently used letters would be longer. Okay, how about like this, right? We can let A equals 0, B equal 1, 1, 0, C equal 1, 0, D equal 1, 1. Everybody agree that that's you seem confused. You're just skeptical it's not going to work, it's not going to compress the data. Yeah.
Are they sending each letter individually, or how do they know?
Yeah, you can send each letter individually, right? So you can have space between the letter.
That's not a bit.
No, because it would be time.
So we're time delineated, okay.
Why not? I mean, yeah, imagine like I'm sending Morse code, right?
Also, if you send no symbols every drop. then since they're all basically don't have any clashes.
Yeah, they are all unique. At the end of the day, you should not have any clashes. Good. Okay, well, here's our same message again. Okay, now we have C for A just 0, so 0, 0, and then okay, D is a long one. 1, 1, 0, C 1, 0, blah blah blah. Look, now we have, okay, let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 letters, or bits, sorry, 14 bits, 8 letters. So the average length of each letter is 7/4 bits. Right? To see that explicitly, consider the average as being the probability that the letter shows up in bits times the length of the letter in bits, right? That's just what an average is. Here's our probability distribution. And then so, right, there's the adding fractions bit that I warned you about. Takeaway from this is that 7/4 is less than 2, so Alice has compressed her message. Good. Okay. Now it gets a little scarier because let's think about, okay, there's a connection here between, oops, I don't know what I did. Okay. Between the probability, right? And then the length of the bit. Does anybody see what the connection is? Yeah. Yeah, right. So it's minus log base 2 of the probability gives you the length of the bits. So minus log base 2 of 1/8 is log base 2 of 8, which is 3, and that's the number of bits that we used. Good. So in the compressed form, the length of each letter is log base 2 of 1 over the probability of the letter. Okay, so now I call this little function I. This is the information. This is what information is, right? It's the number of bits I use to encode each letter. That's all information is. It's that simple. Okay, and so then, yeah, this is what this gentleman just described there in the back, right? Here's the information content of each of the letters in compressed form. Information is defined as minus log time, a log of the probability of the letter in the message. And this is what information is. Information is the average length, or the average information. In other words, the average length of a letter in a message is the probability of that letter showing up times the information content of that letter, right? This is just this. This is the same thing, right? Just encoded in a little bit different mathematics. But essentially, that's the entropy of the source. That's what entropy is. It's the average number of bits you need to use to encode a message in compressed form. Yeah.
The trick on understanding, if you were doing like a base 4, you use 12.
Yes. But I mean, generally, if you're doing statistical mechanics, you're going to use base E. Yeah. Obviously, all of this can be, generalized to natural logarithms and continuous variables. Right? We're doing discrete variables in base 2. You can use continuous variables in any base log you want. It's still going to all work. Right. So this is like Shannon's idea of entropy. Right. Okay. So again, like I said, the idea of thermodynamics and statistical mechanics and temperature and pressure and all this stuff, and even the idea of we think there's this quantity called entropy came before this, but Shannon was like, put his finger on it and was like, this is actually what information is this is what entropy is in terms of information and data compression. And all of this can be used to describe statistical mechanics, which I think is the sort of mind-blowing aspect of it, right? And we're going to get into that more now. How do we talk about physics instead of just, Alice and Bob sending a message? How do we talk about this in terms of physical systems? Okay, well, instead of letters, we're going to talk about, energy levels or particle numbers, or I don't know, fill in the blank, whatever you want. Here's my idea. We have 3 boxes, and we say that each box is, they're all similar. They're all the same. They're not unique, right? So we can't really tell the boxes apart. And each box has some energy value in it, right? So let's say that they could each have particles in them, and the particles are each 1 EV. Do you guys know what an EV is? Exactly. They each have 1 Tesla. Oh, wait, but Tesla is also a unit of energy, so that could be true. All right. Yeah, the EV is an electron volt. So basically, like the size of 1 electron is in each of the, well, it could be, right? And then let's say, okay, say there's different, we could have 0 EV, we could have 1 EV, right? Et cetera, et cetera. And then we're going to say, but the one constraint we're going to put on our system is that the total energy is 3. And it has to stay the same, right? So this is just real generic energy conservation. There's 3 EV in this system. However, and the EVs get distributed in quantized EV chunks, but they could be in any arrangement, right? That's the idea. Okay. So how many configurations can we get out of this setup? By configurations, I mean, how many unique ways can I put these boxes if they each have 1 joule? Oop, it shouldn't say joule, it should say EV. Whoops. Okay, well, sure, joule. Okay, they each have 1 apple in them because a joule at a meter is about or an apple at 1 meter high is about a joule. I guess that's what Tyler told me. Take his word for it. But okay, so they each have whatever, 1 unit of energy in them. How many unique configurations? This is where I want to say I'm going to call this a setup, and then how many unique ways I can make this setup I'm going to call a configuration. So keep those terms separate, right? So how many configurations can I get out of this setup? 1. Why? Yeah, well, all the boxes are identical, so I can switch the boxes around and it doesn't matter, right? So there's only 1 way of setting this guy up. Cool, 1 configuration. What about this one? Yes, I agree. Yes, 3 configurations. Okay, you guys seem like this is so easy, you're bored. All right, well.
I'm enjoying that a little bit.
Okay, well, we'll talk about Lagrangians in a second, don't worry. An imaginary time. All right, so what about this one? This one's a little trickier. Not 8. Well, let's think about this. I can have this in 3 different places. There, there. And in every one of those places, I can swap those around. So it's 3 times 2 times technically 1, right? It's 3 factorial, 6. Everybody see that? 6 ways of arranging this guy. Okay. Now, how would you use entropy to describe these systems? Well, in actual physics speak, each possible configuration is called a microstate, and they're labeled by this lambda, or no, sorry, omega. This omega, big omega. Okay, cool. Now, imagine we assigned a letter for each microstate, aka configuration, so the universe could send a message about the configuration of the boxes. How many bits per letter per configuration do we need for each setup? That's the question. Well, the first one only has 1 state, so we only need 1 bit of information. No, we don't. We need 0 bits. There's only one state, so there's nothing to communicate there, right? So log base 2 of 1. Right? Okay, I'm skipping a step here. What's the probability of finding? Okay, let me go back. Okay, this guy has 6 configurations. What's the probability of seeing one of those unique configurations out of this setup? 1/6, right? So this one is 1/1, right? And then if we did that thing where we said, aha, the probability of the thing showing up, right? The probability of the ensemble showing up times the log of the probability is the information content, right? So if this one has only one possible configuration, then 1 times log base 2 of 1 is 0. So the one that has one possible configuration has no information content. It's like if you watch the same reel of news over and over and over and over again, are you ever gaining any new information? No. Okay. Well, what about the second one? It's had 3 microstates. So we need to describe each of those microstates uniquely. Okay, well, log base 2 of 3 is not really going to give us an even number, but still, if we use that same formula for what information is, it has, we need about 1.5 bits to describe the second setup. And then the third one has six microstates, so we need about 2.5 bits to describe that state, right? So at the end of the day, what I'm trying to say here is that this configuration right here has the most number of microstates, right? The probability of seeing those microstates is 1 in 6. So it takes the most information to describe this state. So what can you say about the entropy content of this state? It's the highest. Yeah, right, exactly. So if there's 10 total configurations, so now we have to zoom out. Okay, I was looking at each setup and I was looking at the configurations of all the setups, but now just thinking about the whole thing, all right? Now go back to this is just a physical apparatus that's just 3 boxes and they each have some energy in them. And I'm not saying that there's any physical laws at play. I'm only saying the energy comes in discrete packs of 1 joule, I guess, in this slide, sorry, right? And it's allowed to go between the boxes and that the total energy stays 3. There's no other physics at play. But given that, we can say, look, there's 10 total configurations. We find the first configuration 10% of the time. Whoa. Hold on, sorry. I lost my key. Oh. Wonder if I just hit no. Tyler, I'm confused. I don't know what happened. I like clicked out of my, should I just stop my share and
Yeah, because you paused it. Yeah. You want to stop share?
So joule's approximately an apple that's held 1 meter above the ground.
guess
So MacBook Air or like MacBook Pro, which ones?
I think it's like an air. I think dropping Apple computers from said heights is a fantastic experiment. I'm sorry, you guys, I have to like completely like re-pull up my little thing. Yeah.
Yeah, but like, computing is all very not. That's what I said. It was just so streamlined. Well, there's some of these cases they switch more and more their pros, like the full desktops to their ARM.
Okay.
Like the sound cards.
Okay, we're back. Okay, yeah, back to this mind-blowing stuff. The second one shows up 30% of the time. It has 3 of the 10 configurations. And the third one shows up 60% of the time. It has 6 of the 10 configurations. What I'm trying to say is given no physical laws at all, I can tell you that by statistics alone, I'm most likely going to see this state here. which has the highest information content. Right? This is the big idea, right? Okay. By probability alone, we're most likely to find the configuration that has the most microstates, i.e. the state with the most information. Okay. So, okay, I do the entropy content for each setup. First one's 0. If I add the first setup to the second setup, okay, I get a little higher entropy. If I add all 3 setups together, I get the highest entropy. Okay. The point being that if I want to include all of the microstates of the system, that's going to maximize the entropy. So if I didn't know what the microstates of the system was, and I wanted to calculate just a physical parameter, I could say, okay, well, this whole little story that I've just told tells me one important thing, which is that the entropy is always maximized. So if I take my generic formula for entropy and I, well, do some calc stuff to it, which we'll talk about in a second. Yeah, okay, I already said all of that, right? This is what I just said. I know that I have to maximize my entropy, right? Based off of my little argument that I just made here. Okay. I guess I was getting ahead of myself. Yes, this is the idea. This is something you guys have all heard before, that, you know, entropy is always flowing upward, right? You can't reverse entropy. This is what the flow of time is. This is why, you know, you can't flow from cold to hot, but only hot to cold, right? You've heard all of these things. But what I'm trying to tell you is that the underlying principle behind all of that physics, which apparently is, you know, the arrow of time and the heat death of the universe and all of those things, is just statistics. There's no physical laws at play. Okay? Which I think is very interesting. So, you know, I also, you know, I was just sort of reading stuff on the internet about what people said about entropy on the internet, right? On sort of forums where people can speak loudly, like, you know, they know what's going on, but they're most of the time wrong. A lot of people say that, you know, heat flows from hot to cold justifies the statement that entropy is maximal. Right? But did I talk about heat going from hot to cold? No. You can take what I said and you can apply Lagrange multipliers. I don't know how many people have taken Calc 3. All right, well, you can, thank you. All right, yeah. Yeah, okay, good. There's another thing called Stirling's approximation and Lagrange multipliers. If you want to see this stuff it worked out, let me know, because I have good notes of it, okay? But you can do this Calc 3 based stuff, and you get this thing that's called the partition function, right? And with the partition function, you can describe all of the state variables in statistical mechanics. You can describe entropy, pressure, temperature, free energy, chemical potential, blah, 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 blah. So you get a ton of physics out of this. As far as, you know, theoretical physicists are concerned, you get all of the physics out of this, right? If you can give me all of the state variables of a system, I know everything that can be known about that system as far as our current, you know, science is concerned, right? And again, I didn't use any physical motivations other than energy was concerned, right? And maybe the caveat that if the universe talks to itself, it does so in the most compressed way possible. Those are the only assumptions that I made. So with this partition function, we can generate what are called path integrals, which are the main machinery that we use in quantum field theory. So if you want to write down a fully relativistic quantum theory, you use a path integral, and that path integral fundamentally is a partition function. And that idea is fundamentally described from this concept of entropy that I just told you about. Path integrals are used to derive the standard model of particle physics. I'm sure you guys, who knows about somewhat about the standard model. It's, you know, you hear about like the strong nuclear force, the electroweak force, electrodynamics, right? And then there's gravity. Gravity doesn't really fit. But we have the other, you know, the stuff that they test at the LHC, looking for the Higgs boson, you know, all that kind of stuff, right? Is there supersymmetry? Is there dark matter? All these things, right? These are all, you know, this is all standard model physics. That all comes from path integral formulation of quantum mechanics. Cool. Well, like I said at the beginning of my talk, path integrals are relativistic. They contain no quantum states, only classical Lagrangians and imaginary time. Further, the only physics that's really constraining the Lagrangians are symmetries. So you take a generic Lagrangian, you constrain it with some symmetry, and it gives you electricity and magnetism. So all it is pure statistics with symmetry sprinkled on top of it. So at the end of the day, this is how I see the universe. You know, there are probabilities and there's symmetries that constrain them, like how the geometry of dice controls the 1/6 probability of each side. If you weigh the dice, you break the symmetry and you alter the statistics. I see there as well, nothing else. Right? I know, I'm agnostic. I don't believe in physical laws. Anyways, so this is where my research begins. Evaluating path integrals, like I said, this thing Z over here. This is the partition function. The partition function can be derived using the concept of entropy and then making the constraint that entropy is always maximal using Lagrange multipliers and Stirling's approximation. This is a path integral that I came up with to describe, conformal field theories in 3 plus n dimensions, right? 3 plus 4 n dimensions, like I showed on my beginning talk there. So, so my research involves solving these infinite dimensional integrals like this one, which I would actually argue is really just Calc 2 turned up. So I make the argument that if you can do Calc 2, and I guess maybe you need to do a little bit of Calc 3, and you can understand the partition function, and you probably need to at least know what an operator is at some point, but we'll eventually get rid of those. But if you can understand that stuff, you can do research in quantum field theory too. It's really, yeah, there's a lot of jargon and it's a big mess, but you kind of just duck and roll and ignore all of that and get to the math, right? Just, yeah, okay. So my group, we look for new perturbative methods of solving path integrals, in particularly in hopes of gaining insight into quantum chromodynamics, which it describes the strong nuclear force, perturbation theory of perturbation theory in normal field theories typically involves a perturbation around this coupling constant lambda here. That coupling constant does not perturb well, if you will, in quantum chromodynamics, because it doesn't stay small, right? If you want to do a good perturbation around a parameter, you hope that that parameter stays small so you can Taylor expand around it. That breaks down in quantum chromodynamics. So there's a whole host of unsolved problems in quantum chromodynamics. One of them is, you've maybe heard of the Yang-Mills mass gap equation, right? It's one of the Millennium Prize problems. Nobody? Okay. Well, there's a lot of we don't know like what happens, like all the phase transitions of quantum chromodynamics. It's a big mystery yet to be solved. So also, fun fact, I don't know, in the 60s, 70s, 80s, right? Quantum chromodynamics didn't really exist yet. And trying to describe the strong nuclear forces where string theory came from, right? Because most particles in nature, when you bring them together, the force gets stronger. But in quantum chromodynamics, when you pull them apart, the force gets stronger. So it's as if they're connected with strings, right? And if you pull them far enough, the strings break, and then you have two new pairs of strings. So that's why the nucleus stays together like that, right? So there's string theory, and then there's quantum chromodynamics. And well, quantum chromodynamics has made physical predictions that have been tested. So anyways, that's the end of my talk. Many thanks to CU Prime and Tyler, the creator of CU Prime. Many thanks to you for listening. I hope it was worth the pizza. And this is the thing I was supposed to put at the end. So thank you.
Wonderful. Well, if you want to help us get feedback from this talk, we have a link here. Feel free to fill that out and tell us about how you think we did. I'll just point out I did not create CU prime. It's been around since long before me.
Whatever.
Thank you for the kind words. Yeah, so we have plenty of time for questions. So anybody have any questions for Seth? You can, yeah, I'll let you take control.
Yeah. Hit me. Huh?
I mean, do you want to drink water or can I ask a question?
We can do both at the same time.
When you mentioned about the Alice experiment at the very beginning, when Alice expresses a message, does that mean that she uses any kind of information?
Well, the information is just the number of bits per letter that she's using.
So say if that was a real sentence or a real word that she was supposed to send using the text or something like that, would she be losing any kind of information in the process of compressing the data or something like that? Or
No, all she needs to know is the probability distribution of the letters showing up in her message. And then she compresses accordingly to that probability distribution. And the length of the number of bits per letter is what's defined as being the information. Yep.
Seth, if
Yes.
there are no states in the partition function, how do you ever calculate anything observable?
If there are no states in the partition function, how do you ever calculate things that are observable, like pressure?
Yeah.
And you just do the integrals and you get the pressure. I mean, next question. Yeah.
You said that in this universe, communicates with itself using the most compressed message. What would happen or what would change if
It would be a very well, standard statistical mechanics wouldn't hold. And I think it would be a very inefficient universe. I also personally believe that sort of there's good reason in that you can go further with this idea of, you know, the universe is fundamentally optimized, right? And I think a lot of the weirdness of quantum mechanics actually also comes from this idea of optimization, that being like, if the universe really does have to sort of know, you know, if there really is information about this thing happening here and this thing happening over here, how do we make that information minimal? Well, if I had to tell you the position and the momentum of every single particle, that would be a very computationally heavy task. So perhaps there's something in there about why the information doesn't go around, you know, keeping tabs on every infinitesimal movement of every particle. Yes, Tyler, the creator.
So you said this was the most efficient way of encoding. I feel like I could do better.
Okay.
And I want you to tell me why I'm wrong.
Well,
This specific example, for
okay.
example, you could get 5 for this bits per letter.
How?
If you say that C is just 1, and then B and D are 10 and 11. So like what's going on there?
C is
For this example, yeah. But this is all.
So A is 0, C is 1, B and D are 1, 0, and 1, 1 respectively.
okay, sure. Maybe that would work for this example, but Shannon proved these things. And I'm not going into that, but there are proofs why this is, you know, why this definition of entropy works as maximally compressed data.
Well, you say you proved it, but.
No, I didn't prove it. Shannon did.
5 forces, 7.
Yeah, yeah, okay. I don't know. But there are mathematical proofs about this.
Well, I think just for this, if you make C1, then you do have this problem where you can't deviate between symbols.
That's true too.
They're chosen such that if you know you're starting at a like dollar point in the
That the string is unique.
that the string, yeah,
Yeah.
always encode to it.
Yeah. I agree. But there's also mathematical proofs of why this works in log base E for continuous variables, which is, I would think, the better way of seeing it, but
Is this definition of entropy one of like a
Yeah. Yep, except you're you're working with density matrices, right? You're working with rho. And it's log, it's rho log rho. It's von Neumann entropy. What?
Well, since you didn't take my previous question, is the path integral unitary?
Yeah.
Then
You can see this by looking at the spectral function of the path integral.
yeah, then let's see.
But that has nothing to do with states. It only has to do with the probability distribution of the path integral. It just means that, the probability distribution of the path integrals describing these statistical variables is conserved.
So then doesn't that mean though that every possible microstate is realized?
Eventually, I would imagine.
So many worlds.
I'm not seeing the connection there. I don't understand why we would need an infinite number of universes unless you believe in superdeterminism.
Okay, you're just the church of larger open space.
Yeah, right. I mean, I think if you look at it as this is just purely statistical things that are just, I'll give you the, yes, if they are, if they're in this statistical state where they're not yet defined or they're not yet realized, they're in this ambiguous probability state, right? But I don't think they all need to be realized simultaneously. They can, the universe can truly be random, and things can go from being not defined to defined, or we can go from, hey, there's no particles here to, oh, now there are particles here. They just sort of, at the end of the day, it's sort of magic. I don't know, but I don't think you do or do not need more than one universe for that to happen. It's equally strange either way.
Well, I guess the point is if it's unitary, I'll just wait long enough until it's in, low entropy state.
If the path integral is unitary, you'll wait long enough till the universe is in a low entropy state.
Yeah. And I think what's the increase?
I mean, is that possible if you have ergodic mixing?
Well, that's the question is that's outside of unitary dynamics.
Oh, well, I don't think that the universe is unitary.
Oh.
Not at all. I'm saying all of the quantum field theories that we work with are unitary. I don't think that's a physical condition at all. Yeah, anybody else? Tyler?
You mentioned imaginary time. What the heck is that about?
Well,
Field?
no. So Helen lives in imaginary time. She's just going through a phase. Yeah, no, it's this thing where you take time and you make it cyclic, right? And it's an artifact of the path integral. But there's another way of thinking about imaginary time, which is that, okay, if I had time and then 3 spatial components in a vector, and then time and 3 spatial components, and I wanted to take the dot product of those 2 vectors to get a scalar quantity that's invariant. Well, if time was imaginary and I took the dot product between the 2 of them, then the overall sign would be negative on the time component of that scalar product between those 2 vectors, and that would give you special relativity. Quantum field theory is manifestly Lorentz invariant. Anybody else? Oh, wait, we got one more.
You mentioned phase transitions.
Yes.
QCD, can you elaborate a little more exactly?
What phase transitions in QCD are?
Yeah.
We don't know, but at some point it goes from being the quark gluon plasma to having this thing we call confinement, which is where the quarks actually make, protons and neutrons and glue balls and whatever. They actually make nuclear matter, right? So when we're at the LHC and we collide the nucleus of gold atoms for a very, 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 very small fraction of a second, it reaches a temperature that's, close to the, very, very infinitesimal, beginning of the Big Bang, where we have this quark gluon plasma and it hasn't confined into actual neutron matter yet. So if we could describe what that stuff is, the phase transition is going from being the plasma to nuclear matter. So from being a plasma to being particles.
So in the mathematical framework, are you use that?
What is it?
Are you dealing with any discontinuities in the mathematical framework?
Yeah, well, for there to be a phase transition, there would have to be some discontinuity in the pressure or something like that. Would give you a, you know, first or well. Yeah, wait, discontinuity in the a crossover in the pressure would give you a first order phase transition. A discontinuity would give you still a first order, right? Right, second order means there's a discontinuity at the second derivative. Yeah, I don't know. Yeah, some sort of discontinuity at some level of derivative. Actually, I think the idea of phase transitions is sort of ill-defined. They go, if there's a discontinuity in the first order, or at the first derivative is first order, and any discontinuity at any derivative after that is second order. I don't know.